Video 4-4, looking at electron configurations for ions and noble gas configurations. Okay, so by now, hopefully you've had good practice at figuring out and writing electron configurations. Now, those were all for atoms. What happens if we do one for an ion? Okay, write the configurations for these. Pause the video. Okay, just do the atoms first, so do these. Okay, pause the video and come back when you're done. Okay, so for sodium, you should have had this. Okay, now, when you do sodium ion, don't forget, you can only play with electrons. So to make it +1, basically what you have to do is lose one electron. Okay, so the one that you lose has to be in the highest energy level, so it should just be that. Okay, magnesium should have been easy. You just had one more than sodium, so it should have been 3s2. Mg2 plus means you now have to lose, again, since it's a positive ion, 2 electrons. Okay. Oxygen was 1s2, 2s2, 2p4. When you have a minus ion, that means you have to add electrons. And since it's a -2, you had to add 2 more. They can go into the p orbital, and you should end up with that. Okay. Fluorine, one more past oxygen, so that should have been simple. And it's a -1, so you're only going to add 1. Okay. And neon should have been that. Okay. Now, you should have noticed a couple things. This configuration, this configuration, this configuration, this one, and this one are all exactly the same configurations. Okay. They are isoelectronic. If an atom or ions have the same electron configurations, they are isoelectronic with each other. Okay. So, what did you notice? These two were in the same row, they're right next to each other. They produce the same configuration as neon, but if you look on your periodic table, this is the row above sodium and where magnesium is. Okay. Oxygen, the oxide ion and the fluoride ions have the same isoelectronic with neon, but they are in the same row. Okay. So cations will be isoelectronic with the noble gas that is in the row above it. Okay. Anions, negative ions, we end up being isoelectronic with the ones that are at the end of their row, not the row above them. Okay, end of their row. Okay, now, noble gas configurations. When you had to write out the configurations for some of your ions, it turned out to be kind of really long. Okay, noble gas configurations are not just for writing the configurations of noble gases. It's for writing for any atom or ion electron configurations. Okay, so arsenic, not too bad, but still kind of long. Okay, now from the end of last lecture, when you wrote out the electron configurations, this was the configuration for helium. This was the configuration for neon. Okay, this was your next electron noble gas configuration. Notice the noble gases all end in P6, except for helium, which is ended in an S2. Okay. Remember that all your noble gases should pretty much end in P6. Okay. So the shortcut method for doing this, in place of writing all of this stuff, in place of writing all of this, we just write in the noble gas. Okay. We replace 1s2, 2s2, 2p6, 3s2, 3p6 with just argon. That's the configuration for argon. Then the rest of this stuff has to be written down. Okay. So arsenic, the way you should be writing out configurations for the element. List the element, colon, and then write out the configuration. Okay. This takes the place of the 1s2, 2s2, 2p6, 3s2, 3p6, then the rest of it. 4s2, 3d10, 4p3. Okay, write the noble gas configuration for calcium. Okay, you should end up with argon, which is the noble gas in the row right above calcium, and then you only have 2 more electrons past that, and they go into the 4s2. Okay, now you cannot use a noble gas for itself. In other words, if I told you write the noble gas configuration for argon, you cannot just simply write argon. You have to pick the noble gas in the row above it, then add in the rest of the electrons. There's 8 more past neon, so they go into the 3s2 and then the 3p6. Okay, now you don't need the Aufbau diagram. Okay, this is the secret. You can actually just use the periodic table, and the only thing you need to know is where it is located on the periodic table, on the chart. Once you know that, you can figure out the electron configurations. Okay, so what's the relationship between the periodic table arrangement and the Aufbau diagram? Okay, this is the cool stuff, so pay attention. Okay, here's our periodic table, here's our Aufbau diagram. Okay, each one of these blocks represents 1 electron. Okay, don't think of these as blocks as like on the Aufbau diagram. Each one of these basically just holds 1 electron in it. Okay, just think of the blocks in the periodic table as electron holders. Okay, so let's say we wanted to go figure out what's the electron configuration of this element right here. Okay, and we don't even need to know what it is. You just need to know where it is. Okay, so this one will have 1, 2, 4, 6, 8, 10, etc. This many number of electrons. Okay, put 1 electron from here, or 1 electron in each box. Okay, now these, you know, have to go into the Aufbau diagram. Okay, so we'll start putting them in. We'll move them from here down to here. Okay, so the first one goes there, the next one goes in there. Okay, this next electron here goes into the next orbital. The next one goes there. Okay, remember your rules, make sure they're opposite spins. Okay, the blue ones, there's 1, 2, 3, 4, 5, 6 of them. And they go into the p orbitals, which just happens to be able to hold 1, 2, 3, 4, 5, 6. Okay. Next 2 electrons go into the 4p. Then we run into these blue ones again. 1, 2, 3, 4, 5, 6. Okay. Then we have the 4 s's. Those can hold those 2 electrons right there. Okay. Now, all of a sudden you run into the transition metals. Okay. But, kind of weird, look, the 3Ds are right there. And they can hold 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there's 10 across. Okay. Then comes the 4p. 1, 2, 3. Then we start pairing them up again. 4, 5. Okay. Now, what did you notice about all this stuff here? Okay. Notice all the red ones always went into s orbitals. All the blue ones always went into p orbitals. Okay. All the green ones, which were this section here, this was always green. This section here was always red. This section here was blue arrows. Okay, all the blue arrow sections always went into p orbitals. The green arrow sections went into the d orbitals. The red arrow sections went into s orbitals. Okay, so these sections right here, these 2 blocks, basically any electrons that are there go into the s orbital. So these are the s blocks, okay, except for that one there. Okay, these are the p blocks. Anything in these sections here always went into p orbitals. These were the d blocks. Okay, and we didn't use anything down here, but notice there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of them. And things that can happen to be able to hold 14 are going to be f orbitals. 11 orbitals, each one can hold 2. Okay, elements in the same family always end up with the same outer electron configuration. The outer electron configuration is known as the valence electron configuration. Okay? In other words, all the halogens, because they were in the same family, always would end up with a P5 configuration. Okay, now, how do you figure out what number goes where? Okay, well, the first two electrons went into the 1s. The next, these two electrons went into the 2s. The ones here went into the 3s. These here went to the 4s. So, how do you figure out what row and what energy level they go to? Well, the s blocks, if they're in row 1, they go into the 1s. So it's the same as the row number, the energy level number. Okay. These went into the 2s. These went into the 3s. These are in row 2 and row 3. So their relationship, the p blocks, they are also the same as the row number. These went into the d block, but these did not go into the 4d. These went into the 3d, but this is in row 4. Okay. So the relationship between what row the d electrons are in and the energy level is the row number minus 1. Okay. Now, this is the first time we're going to start putting in things into the f orbitals, but these go into the 4f, the ones that are in row 6. Okay. So their relationship is the row number minus 2 will tell you what the energy level is for the f electrons. Okay. So how do you do it really fast? How can I just look at the periodic table and rattle off an electron configuration without doing anything else? Okay, it's really simple. Okay. You can also use the noble gas configuration and just worry about the configuration of the last row that the element is in. Okay. So, using only the periodic table, write the electron configuration for iodine. Okay. You can pause the video, write it out, and see if you get it done, and come back and check. Okay, so here's iodine. Okay, we're going to do the shortcut method. Just figure out the noble gas. So you don't have to worry about any of these things up here. Okay, all we worry about is the ones that are in the last row, the 5th row here, up to iodine. So find your first noble gas, which is the one in the row right above it. So we start out with krypton. Okay, then we have to worry about where these electrons go. Okay, so these two are in the s block, and they're in row 5, so they go into the 5s. Okay, and there's 2 of them. These are the d blocks, right? But don't forget, it's the row number minus 1, so these are not going into the 5d, but the 4d. Okay, so it's 4d, and we fill them all up, so it's going to be 4d10. Okay, and these go into the p orbitals, and the p's are the same as the row number, or in row number 5. So they're 5p, and there's 1, 2, 3, 4, 5. Okay, so it's 5p5, and that's it. Okay, what if I told you write out the whole long thing? Okay, simple. Start at the very top, work your way left to right, and fill it in. Okay, and write down the full configuration. So, in other words, we wouldn't be starting from here, we'd be starting from the top. Okay, work your way across the top row. That these two have to go into the 1s, and it's 1s2. Next two go into these are s blocks, 2s, so it's 2s2. Those are going to be the 2p, and it's filled, so it's 2p6. Then 3s, 2, these are p orbitals. They go into the 3p, 3p6. Those are going into the 4s. Okay. Here's our d blocks. They're in the row number minus 1, so it's going to be 3d. Then we have p blocks again, 4p. Okay, and then it's basically the stuff that we just learned before. 5s2, 4d10, 5p5. Okay, so you'd write out the whole thing: 1s2, 2s2, 2p6, 3s2, 3p6, etc. Okay, now watch out for elements that are in row 6 or row 7. Okay, write the noble gas configurations for these elements right here. So that's cerium, lead, and uranium. Okay, so first one, here's cerium. Okay, so we pick the noble gas in the row above it. This is not row 7, this is row 6, don't forget. Okay, so we pick the one from row 5. Okay, so our noble gas here. And then we just have to worry about putting in 1, 2, 3, 4 electrons. Okay, so we start with this element right here, which is xenon. That electron right there goes into the 6s. The second one goes into the 6s. Okay. Now, be careful. This electron right here, the 57th electron, does not go into the 4f. Look where this box is positioned. This is basically in the D block. Okay. So, the 57th electron actually goes into the 5d. And then the last electron down here, the 58th electron, goes into the 4f. These are the F blocks. Okay, so these electrons right here, watch out for them. Okay, now, even though the 4f is lower than the 5d, we actually write it last. We don't write it as 6s, 6s2, 4f1, 5d1. You write this one last. Why? Because if you write it correctly, when you look at the last thing, you should be able to figure out where the element is located. You should say 4f. Oh, so that's in the row 6 in the F block, and it's the first one. Okay. Now, the book and most periodic tables will not write it this way. They have to write it this way to figure it out, but then they will go 4f1, 5d1, 6s2. Okay, this is not the arrangement. They just rewrote it by rearranging it by smallest energy levels first. Okay. Now, if I see you do this on the test, I know you cheated because you cannot get this without getting that first. Okay. So be careful when you see it this way. Okay. Our next one was lead, right down here. Okay, so again, we pick the noble gas in the row above it, and then we have to put in these electrons. They go here, they fill up the bottom, then they start filling up these again, and then those two. Okay, so the first two go into the 6s. This 57th one still goes up here. Then you start filling up 58 all the way down to here. Okay, then you fill these up again. Rest of these go up there, and then the last two end up in the 6p. Okay, now, once you're done, look at the whole configuration, okay, and write it out from bottom up. 6s2, 4f14, 5d10, 6p2. Okay, and we don't care that this one filled up first. All we care about is once you're done, that it's completely filled. Okay, and the last one we want to look at, this one was uranium down here. Okay, so this is row 7, so we pick the noble gas up here in row 6, radon. Okay, then we have 1, 2, 3, 4, 5, 6 electrons. Okay, so those two go into the 7s. This one here, remember, is not in the F, it's actually in the 6s. Or 6d rather. Okay, and then we have 3 more in the F block. And it's the row number -2, so it's going to be 5f, 5f3. Okay, and again, even though this is actually lower than this one, we write this one last because that's where the last electrons went. So here's the review. Which of the following is not correct for electron configurations that are derived from the periodic table?